Hi class, we are on chapter 9.2 now. We are going to discuss isomorphisms today. Okay. An isomorphism is when we have two different vector spaces that are essentially the same. Okay. So for instance, you probably have seen this when we've been doing work, but for instance, like let's say we have a vector in the 2x2 real matrices space. A lot of times when we want to work with that space, we will transform them into column vectors in R4. Okay, so that's an example of an isomorphism where we can take a vector from one space and kind of morph it into another space and do essentially all the same work that we would do in the first space, right? So that's what an isomorphism is. We do this a lot with polynomials as well. A lot of time we just take the coefficients from the polynomials and then we turn them into column vectors, right? So, and then we work with our column vectors. So for instance, P2, we can turn into a column vector in R3. So those two spaces are isomorphic to each other, right? So for instance, again, R4 and R 2x2, right? So 2x2 real matrices and the column vectors of, with 4 entries, they're basically the same thing. Okay, anything I can do in here can relate to something that I'll be doing in here. Is also isomorphic in this case to P3, right? So let's go over the formal definition of what an actual isomorphism is. So if we have a linear transformation T from a vector space V to a vector space W, it is an isomorphism if T, this transformation, is both one-to-one and onto. Right, so that's basically it. So as long as this transformation is a one-to-one transformation and an onto, surjective and bijective, then we'll have an isomorphism between spaces. Okay, so if such an isomorphism exists, then we say that V and W are isomorphic vector spaces. They are isomorphic to each other. Okay, so again, there's a difference between an isomorphism and two vector spaces being isomorphic. Okay, so an isomorphism is the actual transformation, okay, and V and W being isomorphic vector spaces means that they are basically one in the same vector space. Okay, so there's isomorphic versus isomorphic. So if T from V to W is an isomorphism, then there will also exist an isomorphism S that goes from W to V. Okay. So even if T to V, the transformation from V to W is not an isomorphism, V and W may still be isomorphic to each other. Okay, so there just may be another transformation that is an isomorphism. It could be that this transformation is not, right? So there may be a different linear transformation from V to W that is an isomorphism. So in an isomorphism, every vector V in the domain V is paired with a specific W in the codomain, right? And that's because it is one-to-one and onto. Every single vector here maps to a distinct, unique vector in W and so forth, right? So this entire space is mapped to this entire space uniquely, right? So there's a one-to-one correspondence. So this helps to establish that V and W are essentially the same, right? So this is a very important property we're going to discuss right now. So if we have V1 plus V2 being a third vector, okay, then W1 plus W2 is going to be the same thing as the transformation of V1 plus the transformation of V2, which we know for linear transformations is can be split apart, so we can unsplit them apart, you know. So the two separate transformations being added to each other is the same as taking the transformation of just the sum of the two individual vectors, right? Which in this case we know V1 plus V2 is actually V3, so this is really just a transformation of V3. Well, the transformation of V3, especially since it's a one-to-one correspondence, is going to get us out W3. Right? So another way of saying this is that if V1 plus V2 is V3, then their mappings W1 plus W2 will equal W3. R3. Okay. So let's do an example. Right. So we want to show that R2 and the subspace S, which is generated by the span of these two vectors, 1, 0, 1, negative 1, 2, 0, of R3, right? So this is a subspace of R3 because these are two vectors in R3, are isomorphic. Okay. So what we're trying to say is that this space is the same as this space. Okay, for all intents and purposes. So this is a proof. It says show. Okay. So before we even get started, this is how I want you to think about this. Okay. What is the span of these two vectors? Right? We have two vectors in R3. Together they make a plane in R3. What is R2? R2 is just a plane. It is a two-dimensional plane. This is a two-dimensional plane that is a subspace of R3. So since this is a plane and this is a plane, they're basically the same thing. Okay, so that's our idea. And we're going to move forward with this and show that they are isomorphic. Okay, that they're basically the same thing. So to show that two vector spaces are isomorphic, we need two things, right? We need there to be an isomorphism between them, or we need to say that we need a transformation, right? That's what it means to be isomorphic. An isomorphism or an isomorphic means that there is that they're related to each other. An isomorphism means that there's a transformation that is one-to-one and onto between them. Okay, so what we need is we need a transformation between these two spaces that is one-to-one and onto. So a transformation from here that maps onto here, that's one-to-one and onto, or vice versa, right? So let's consider the transformation from R2 to S that's given by taking a vector in R2 and mapping it into this space by A minus B to be A. Okay, so now you might be saying, well, how do we know that this maps onto this space S? Well, look at how we form this transformation matrix. A's, B's. A minus B to B and A. This transformation matrix is all the things that are going to be in this space, right? Because these are the basis vectors. This is the transformation that would be made up by these basis vectors. So to show that it's one-to-one, we have the transformation of some vector x equals A times x, where our transformation matrix, is this transformation matrix, right? So again, when we pull this into the transformation matrix form, it's just going to be the column vectors of the span that creates our subspace. And since the columns of A are linearly independent, we know that the only way for the zero vector from R2 to map to the zero vector here is by using the zero vector, right? That's what it means to be linearly independent. Okay, so x1 times this plus x2 of this equaling 0 has only the trivial solution, right? The only way for this to work is if this x1 is 0 and x2 is 0. So that means that my input here would have to be the zero vectors, right, to get the zero vector out for the subspace S, right, or x is equal to 0. Okay. Therefore, the kernel of this transformation is the zero vector for R2, the zero vector for our domain. Okay, therefore T is one-to-one. Next, I need to show that it's onto, so I need to show that every transformation from R2 maps to and covers the subspace S. So the kernel space of A is the span of these vectors, which is S itself. Therefore, T is onto, right? So all linear combinations of my transformation matrix is really just the subspace itself, right? I did that by design. That was the easiest way to do it. So T is onto. No matter what I plug in here, will form a linear combination of these two vectors, which will map into the subspace, right? So T is one-to-one and onto, which means that it is an isomorphism, right? And since it's an isomorphism between two vector spaces, it means that those two vector spaces are isomorphic. Okay, so it's a pretty straightforward method of trying to show that this is an isomorphism through the definition. Okay, so let's move on to a theorem. Suppose that finite dimensional vector spaces V and W are isomorphic to each other. Okay, so they're just not infinite spaces. There's like R2 and R2 by 2 or something, right? The dimensions have to be equal. Okay, so if these are finite dimensional and they're isomorphic, then their dimensions are the same. Right? So another theorem. Let V and W be finite dimensional vector spaces such that their dimensions are the same, because that's what has to happen, right? They can't be isomorphic if they're not the same. M has to be positive, obviously. So suppose that V is a set of vectors, and W is another set of vectors, and they are bases for their respective vector spaces. So this is a basis for V, this is a basis for W. Here we have not yet said that they are an isomorphism, but we have said that they have the same dimension for these vector spaces. Okay, it's a positive dimension. So the linear transformation from V to W follows, right? So for every V inside of my vector space, my domain, let's say we have a set of scalars such that V can be represented as a linear combination of these scalars, right? Then what we're going to do is we're going to set T of V to be a transformation, right? So T of V means that I'm basically going to transform each of these pieces. First we'll transform the whole thing, and then we'll separate it into pieces, right? So T of V means I transform the linear combination that makes it up of basis vectors. And that's going to be the same thing as a linear combination of the basis vectors using the exact same coefficients, right, or coordinate points that I use to make up for the linear combination of basis vectors in V. It'll be the exact same constants as a linear combination for the vectors, the basis vectors for W, right? Then T is an isomorphism. Okay, so if this property holds, basically this thing here, if this is true, then we have an isomorphism. So now we're relating an isomorphism down to its more to its core structure, which is a basis, right? So T would be an isomorphism. V and W are isomorphic vector spaces. They're isomorphic to each other, and T is an isomorphism between them. Okay, so let's come to our next theorem. Let's say V and W are isomorphic and they are finite dimensional. This is true if and only if their dimensions are equal. So this is a much easier way to show that two vector spaces are isomorphic, just showing that their dimensions are the same. If they have the same dimension, then they're going to be isomorphic. So we no longer have to find a transformation between them that is onto and one-to-one unless we're specifically asked to do that, right? If we're now asked to show that something is an isomorphism, right? If that two vector spaces are isomorphic to each other, all we have to do is form this relationship between their dimensions. Okay, so for our next theorem, if V is a vector space and the dimension of V equals the value of n, then V is isomorphic to Rn. And again, that's just coming from the last theorem, where the dimensions of two spaces need to be the same. Okay. Last definition is that a linear transformation from V to W is invertible if T is one-to-one and onto, right? So again, that's coming from that big theorem. So when T is invertible, the inverse function, T inverse, or the inverse transformation really, T inverse from W to V, is defined by T inverse of W equals V if and only if V gets sent to W, right? So the inverse function basically sends W back to V if V is sent to W by the main transformation. So that's it. Okay, hope you guys enjoy the video. See you on the next one.